First of all, thank you very much to the organizers and for giving me this opportunity. And I'm going to talk about something not so related to quantum cryptography or anything about the cryptography. But what I understand is the quantum computing itself is a kind of enemy to you. So first of all, you have to understand what the enemies are or what they can do. But again, unfortunately, this is not exactly about the quantum computing. It's about its cousin, quantum information. But I think they share the same philosophy of quantum phenomenon. And of course, many people are working both of the directions at the same time. So you'll see something in common, I hope. And I work on functional analysis, operator algebra, and abstract harmonic analysis. So not so close to anything about quantum crypto or the quantum information at first sight, but there has been quite surprising connections over the years. And let me begin with my own personal encounters with the quantum crypto or post-quantum crypto people. So if you look at these two papers, then you can see one of the authors are Regev, and I encountered that name like 6 or 7 years ago, and at that time, I just thought this is some guy doing functional analysis, but I just never met him, but I was completely wrong. So he was one of the guy that could do many things, and it was a very surprising thing. So for example, the paper is about Grothendieck's theorem, and you might remember Grothendieck as an algebraic geometer. Of course he was, but before he moved to algebraic geometry, he actually did functional analysis, and he studied Banach space and tensor products and for a long time, and he felt that there is nothing I can do because it is too difficult, so he moved to algebraic geometry. But before, but his last work in Banach space was really influential. He proved what we called Grothendieck's inequality, and inequality is about finding some relations between two quantities, and usually people care about what is the best constant. And still, there is a mystery about Grothendieck's constant, and people are trying to improve their estimate or find the best constant. And quite recently, less than 10 years, people realized that this Grothendieck's inequality has some meaning in computer science, and they developed their own machinery. And actually, they proved several surprising things. So first of all, what Regev did in the first paper, they gave extremely simple proof about the non-commutative Grothendieck's theorem. I spent a lot of time to understand the original proof, but after 10 years, they gave very intuitive, good enough the proof. And the second one is another paper by Regev and other people, and that's about locally decodable codes, and maybe you don't understand what the other means, like code type of a projective tensor product. This is what Banach space people do. So I remember one phrase in that paper saying that their original motivation was because they knew Banach space theory very well. They really wanted to apply this Banach space technology to coding theory. But their project failed, so they just ended up proving one open question in Banach space theory. Long-standing open question for 30 years or something like that. So now I realize that there are many people in computer science who can actually answer our questions. So this is not surprising. 3 years ago, there was one solution of long-standing open conjecture in operator algebra, which is called Cadison-Singer problem, that has been solved by a bunch of computer science people. But unfortunately, not so sad story, because the other way around is also happening. So these papers are kind of the proof that the computer science people helped a lot, but at the other side, functional analysis been quite useful to quantum information. So there are three instances I actually have been witnessing. The first one is the recent, still recent, the breakthrough about the minimal output entropy additivity conjecture in quantum information theory has been proved using functional analysis techniques. So so-called the concentration of measure phenomenon, or some the old tools in Banach space theory has been used there. And some of my colleagues has been using so-called the free probability to improve their bounds. And secondly, this is really my field. There has been some attempts to use what they call operator space theory. So here operator means linear bounded operators acting on some abstract Hilbert space. But they realized that this abstract theory can be used to prove something about Bell inequality. So Bell inequality is to get some bounds between some walls between the classical world and the quantum world. And there are many Bell inequalities, and there are many experiments about that. And what they did is they used operator space theory to show that in tripartite, or when three bodies are involved, then there is no usual upper bound for the quantum world. So they actually calculated that the violation of tripartite Bell inequality could blow up. So that's what they proved. But at that time, it seems like it was quite a shock to the community. So in the first version, they used very complicated technology. This Professor Junge has been developing for 20 years. But computer science people were smart enough, so they have much easier explanation, not using any that complicated technology. The third one is actually the theme of my talk today. There are several operator algebra people now jumped into quantum information area, and including Paulson and Todorov, and of course Andreas Winter is the kind of founding the people in the quantum information area, but he understands a lot of operator algebras. There are people using so-called operator system theory. Anyway, we'll be talking about the third one. Okay, so the whole story is about what we call the game theory, but this is slightly different from what you can find on the Wikipedia. So, for example, if you Google game theory, then they will give you a slightly different version. Okay, so this is what they call the finite input-output game, and we have two players, Alice and Bob. So we will use A and B to denote Alice and Bob, and they have finite input sets. So input sets are here, IA and IB, and outputs are OA and OB. You can easily imagine what it means. And we will just use fixed variables, XY for the inputs and AB for the outputs. So the basic assumption is A doesn't know what B's input or outputs, so they don't communicate. And vice versa. B doesn't know what's going on in A's side. But A and B, both of the player, they know the rules. So basically they're a team and they want to play against the referee. So there is a third party, so examining where they are winning or losing. So the game begins like this. The referee gives the input X to Alice and input Y to Bob. Then they just do their own processing and produce outputs A and B relatively, and give it back to the referee. Then the referee decides whether they lose or win. So we use 0 and 1. So they work as a team. So one is good for everybody. I mean, to Alice and Bob. This is a two-person the game. Okay, so let me give you one example of such a game, which is called a graph coloring game. So this is the slight difference from what you can see in the Wikipedia. If you search Google, then they will give you another version of the graph coloring game. This is different version. So here, we are interested in graph coloring problem, which is very well known and interesting problem. So when we have a graph, so that means it's a simple graph consisting of vertex set and edge set. And we are interested in whether we can find a C coloring. C is the number of the colors. So the existence of C coloring is the same as the finding some function assigning for each vertex some colors, and we have to satisfy that the neighboring vertices, they have different colors. So the usual coloring in the graph. But we want to color each vertices. And if we want to use the previous slides, the terminology, the input sets are, both of them are the same, the vertex set, and output sets are the color sets. And so the game goes like this. We have two players, so the referee gives them two vertices, x and y. So we have two vertices, and sometimes they are adjacent, sometimes they are even same. And the winning rule is should be like this. So when they are adjacent, then they should have different colors. But if they are the same vertices, then they should have the same color. So this is the only rule we should remember. So what I'm saying is the famous graph coloring procedure can be understood as a game. So then it doesn't matter. So it is not included in the rule. It wins. Here is what I understand. So if we want to find some coloring, then the practical way to check whether we have a coloring is, if the map is too big, then we cannot see the whole picture at the same time. So there should be some referee giving you randomly 2 points. Then if they are adjacent and we check whether they have different colors or not, then if this happens all the time, then maybe we can regard that, oh, you might have the C coloring I wanted. So that's how we understand this game. Okay, so there's a concept of deterministic strategy for this game. Okay, so let's go back to the abstract setting. And a deterministic strategy means a pair of functions given for A, Alice, and Bob. So the first function f is for each input, it is already determined what to answer. So the corresponding function g is for b. So again, for a given input, then there is no other choice to follow the given function. So we can ask fundamental questions like this. Is there any so-called perfect strategy? If not, then what is the winning probability of this team? Or sometimes we call it value of the strategy. So let me give you some formal definitions. So for a pair of two functions or deterministic strategy of a game, script G. And this is just maybe minor fact for the moment. There could be some given probability density for each input. But if it is too complicated, you could just assume that this is a uniform distribution. So every input is treated equally. Then we call this pair a perfect strategy. So if it happens all the time. So if the team wins all the time. So that means, so this lambda is the rule function. So for a given input xy, we want to examine this fx and gy. They are outputs. And we want this value to be 1. That means all the time they are winning. So this is exactly the situation I explained to you. So practically, if you want to check whether this guy has a C coloring, then one way of doing it is I asked the questions almost all the many times, but the answer is correct all the time. So mathematically, this is just the equivalent formulation. And secondly, we can also define winning probability here. So this is really just expected value of this so-called mapping. So for each assigned probability density, so I told you that we could just assume that this is 1 over the cardinality. And this is the 0 or 1 value. So 0 means they lose and 1 means they win. So this is really just winning probability for a given choice of strategy. But sometimes you are interested in the maximum or the supremum of all winning probabilities. Okay, so let's go back to the graph coloring game. Then the existence of perfect deterministic strategy means it's the same as this graph has a C coloring. Maybe I forgot. Yeah. So here we have C, but this one doesn't have C, but it's apparent that C means the size of the output sets. So for example, if we consider this kind of the simple graph, this is K3, the complete graph of 3 vertices, then it's quite apparent that 2 coloring is not possible, but at least we can calculate the winning probability. So for example, if we just assign this function f and g to be the same, and their values are given in this formula, then we can actually just do the computation to see that the winning probability is 7 over 9. And it's not too difficult to see that this is the best we can do. So even though we don't have 2 colorings, that maybe this is too small, so it's not so intuitive, but you might cheat the referee with the probability of this amount that we have 2 colorings. Okay, so let me give you one more example of a game. This is what we call CHSH, the following the 4 names game, and this is important for quantum information people because we will soon talk about so-called quantum strategy, so some quantum language, but it's very important to actually do some experiments that verifying your claim. But this model is simple enough to do many experiments to back up with the mathematical calculations. So anything what I say here can be actually verified in the lab. So this game is quite simple. So the input sets and output sets are Z2 or just 0, 1 sets. And the winning strategy is already, winning rule or the rule function is known as this formula. So when we have 2 inputs x and y and outputs a, b, then we just check this the equality, and if it is true, then we get 1, or if it is not true, then we get 0. So one of the choice we can easily make is we just choose the identically 0 function. Then that means whatever your input is, you just give 0 as outputs. Then still we have the 3 over 4 of the winning probability. And this game is coming from the CHSH, the same name, inequality. This is one of the well-known Bell inequalities. Anyway, again, this can be verified at the lab. And the reason I'm giving you this example is, actually it is not too difficult to see that we can do much better using so-called quantum way. Okay, so let me proceed a little bit further. So deterministic, the strategy is already, you have no choice. So the players, each players are given some fixed the plan to follow, but there is one more general strategy you can take. So instead of giving you a fixed the map, you can get some probability density applied. Then this is more general than the fixed, the deterministic strategy. And you might hope that maybe we can do a little bit better by doing it probabilistic way. And it is sometimes called local strategy. So this strategy means it's a function for each pair of the input, you want to assign some probability density on the output sets. But in other words, that means for each pair of XY input, you are assigned some probability density on A side only and B side only with the joint probability. So there are some correlations, and that is the point of you are hoping that maybe there could be some possibility of getting better. So for example, this is one example we can take. For example, you decide your output based on today's market value of X company and Y company. But there could be some correlations between two companies, and that's how we explain this probabilistic strategy. And we can define the winning probability similarly. The only difference is we multiply the probability in each choice of the inputs. So again, we can think about perfect probabilistic strategy. That means if this rule function is 0, that means lose situation doesn't happen. So the losing probability is always 0. So this is what it means. So that means, again, you get the winning with probability 1. But in most of the cases, this is discrete. So you actually get a really perfect strategy. But what you can actually prove is, because of the convexity argument, this is no better than the deterministic strategy. But using this formulation, we can go to the quantum world. But before we enter the quantum world, we have to understand what it means mathematically about saying quantum. So let me give you some choices of postulates of quantum mechanics. So first of all, we assume that every physical system is described by a Hilbert space. And this Hilbert space H is called state space. And each unit vector in this Hilbert space is called a state. So some kind of physical state. And the second postulate is we actually have to do or perform some quantum measurements to get some kind of output. And they are always described by linear operators acting on the same Hilbert space H. And it's a family of operators Mi. And I belongs to the set of all outcomes. So you really want to see all possible outcomes. And that is done by applying some kind of linear operators. And there are some assumptions we have to give them. So for example, Pi, the probability of outcome being I, is given by the norm of this vector. So MIH. So you apply this Mi operator to the state H, then it might not be unit vector again. So you just decalculate its norm square. And the sum of all probability must be 1. So we can easily see this equality should be true. So here I did a little bit of algebraic manipulation here. So from the definition of Pi, it is MIH norm square, but you can always use inner product, and using linearity it becomes like this. We will get to this point again. And the third, the assumption is when you actually perform the measurement, then this is the really quantum situation. Actually, your state becomes different, and it changes to a new state, MIH, but you need to be in the unit vector world, so you have to divide by its norm. So sometimes you just want to use this set of or collection of linear operators, but sometimes you want to make it positive. So instead of considering Mi, you look at Mi star Mi. This is positive semi-definite matrix or operators. And its property is always positive, with some being identity operator or identity matrix. And this family is usually called POVM, so positive operator valued measures. So in the case of the classical situation, then this is really the replacement, the right replacement of the probability density. So that's why we call it a positive blah blah measure. Okay, so now I can explain what a quantum strategy means. So quantum strategy means now we have, this is a shared state, so-called a shared quantum state, shared by two players, Alice and Bob. So they are sharing one quantum state, and usually that's entangled, or sometimes maximally entangled. And they have two quantum devices assigned, or in other words, POVMs assigned for each XY to Alice and to Bob. So that's the POVM, or family of positive operators, acting on HA and HB. So HA is the system, physical system about Alice, and HB is the system about B. And the important point is the state is chosen in the tensor product or composite system. So now instead of the probability measure, we consider quantum probability measure. So it's a little bit different now. So instead of doing the summation or something like that, we apply this operator tensor, the X operator and Y operator, or Alice operator and Bob's operator. We tensor them, and we apply this HH. This is the usual way of calculating some the integral in the quantum situation. So we have the quantum version of joint probability. So we follow the same plan. So we define this winning quantum probability, or quantum winning probability, replacing P into PQ. So we can continue to define the perfect quantum strategy. Again, that means the probability or quantum probability of failure or losing is 0. So if this happens all the time, then this is perfect. And quantum strategy can be much better than before, than deterministic strategy. Okay, so this is one thing we can check in the lab. So I'm giving you a little bit of details. So CHSH game, this is, we have two inputs, 0 and 1. And let me go back a little bit. Yeah, this is the CHSH game, and we have a simple winning rule, or a simple ruling function here. And the winning probability using deterministic or probabilistic approach is the same. That's 3/4. But what I'm saying is, you can actually pick a specific choice of state. This is the usual maximally entangled state on the composite system. And you can choose very specific choices of operators, so POVMs, which everything can be reproduced in the lab. Then actually you can check mathematically that quantum winning probability is strictly bigger than this value. So this is some model you can check in the lab. Okay, so going back to something else. Okay, so let me just add a few more things about the graph coloring games. Right, so for example, you can imagine some kind of graph, and it's important to find whether there is a C coloring or not. So this is the question many people want to get the answer, but it might not be possible to get deterministic or the actual C coloring, but the whole story says that in quantum way, maybe you can find some better way of the cheating the referee, to cheat the referee that he might think that I have C colorings. And of course, there are many calculations done. Okay, so let me explain a little bit about the correlation matrices. So when we define these winning probabilities, we used, winning probability, we used this joint probability densities and sometimes quantum joint probability densities, and they are actually coming from the concept of correlation matrices. So now, for simplicity, let me fix the size of input by n and the size of output by k, and then we can consider the following definitions of correlation matrices in various settings. For example, C local, this is following probabilistic approach or local approach. So this is the collection of all probability densities coming from this the each functions. And CQ, this is quantum correlation matrices obtained by the formula we used here. So we pick two POVMs and pick the state in the composite system, and we calculate this the quantum joint probability density, and we collect all of them. And we can apply some more analogies. So here I use QS. This means quantum, but in the separated model. So up to this point, we were concerned about finite dimensional Hilbert space. So basically, it is just Rn or Cn. So no complicated structure. But there is no reason to believe that your Hilbert space or your physical system is described by the finite dimensional Hilbert space. And sometimes, even for photons, you actually have to use infinite dimensional ones. So it is very natural to consider this version of allowing infinite dimensional Hilbert space. But still, you want to use the tensor products separation. Oh, I made a mistake here. And the last one is commuting model. But here, again, it seems like this is a understanding about the fundamental quantum world. It seems like there are some quantum systems that we actually have to go beyond this infinite dimensional but separation. So that means we still want to look at the infinite dimensional operators, but only with the assumption of commuting. So that's the meaning of this C. So quantum, but just allowing commutativity. So I made a mistake here. So this is something else. Anyway, all of those correlation matrices, they are subsets of this particular Euclidean spaces of dimension n square, k square. So, and they are of the matrix form. So that's why we call it correlation matrices. And we already have seen that there is one example that the probabilistic or deterministic is different from quantum world. So we already know that this inclusion is strict. And we can see these, the matrices are in this order. And each correlation matrix gives you corresponding strategy. So we had quantum strategy coming from this quantum correlation matrix, but we can consider QS, or quantum separation model strategy, or quantum commuting strategy. So that's also possible. And we can define winning probabilities similarly. Yes, CQA is defined by the closure of CQ. So this is the closure of just quantum in the Euclidean space. So in other words, this is A means approximated. So this is some model approximated by finite dimensional models. Anyway, so this is the moment of going to the operator algebra a little bit. So now, in 80s, the Boris Girasant gave the conjecture, or at that time he considered that he had a proof. So he claimed that he has a proof that CQ, this correlation matrix set, is the same as CQC. The commuting model is essentially the same as finite dimensional quantum model. But it turned out that it is not true right now. There has been quite recent breakthrough by Slofstra saying that we could find some the perfect strategy in this commuting model, but not in this quantum model. But anyway, this is some old conjecture people have been working on, but there has been some progress right now. And more interesting conjecture is Kahn's embedding conjecture. So this guy is Alan Kahn, the Fields medalist, doing the non-commutative geometry these days. But in his 70s work, he made one conjecture. But it turned out that this is equivalent. So this is purely operator algebraic conjecture. And it is known now, it is equivalent to this approximate system is the same as the commuting system for all nk. So very surprising connection to operator algebra. Maybe a few more words on both of the conjectures, then it's almost the time. Okay, so let me just go directly to the second one. So Kahn gave his conjecture in 76 paper about the injective factors. He gave the conjecture saying that any separable type 2-1 factor embeds in the ultra power of blah, blah, blah. It's really just the operator algebra people can understand, and they care about this one. So I'm not going to explain what this means, but this is purely operator algebraic statement. And people thought about this one over and over again for a long time, but there is one famous equivalent formulation by Kirchberg saying that this statement is true if and only if there is only one so-called C-star norm on this tensor product space. And here we are looking at this free groups with infinitely many generators, countably many generators, and there is a natural way to make it so-called C-star algebra. This is one object we study in operator algebra, and people cared about whether how many C-star structures on this algebraic tensor product, and it turned out that these two statements are equivalent, and there are many more equivalent formulations regarding this conjecture. And still, people believe that there could be some hope using this quantum information understanding or fundamental understanding about the physical world can be related to this operator algebra problems. Okay, so I'll stop here, and thank you very much for your attention.
Okay, thank you. Question or comment? Yes.
Can you go back to the previous slide, to the Tiersen's conjecture?
Yep.
So from CQ to CQC, we know one of the containment is proper, and I mean at least one of the containment is proper.
Yes.
By
yes.
The new result by Slovstra.
Yeah.
And what's your like? What would you conjecture? Like, are all three gonna be proper or just one of them?
Yeah, I think there are many people believing that this Kahn's embedding conjecture must be false.
So like
yeah.
all of them are proper? That's
yeah.
People you really believe?
Of course, there are some people still believing in the positive directions, but there are many people also. I have no idea. I never spent any serious amount of time to doing this. Of course, you can understand these things are quite dangerous to try. So.
All right, thank you.
Quick question. Does anyone happen to think about it, use this strategy to conduct the quantum simulation?
I don't know.
For instance, to solve the optical
well,
optimization problem?
yeah, this is, unfortunately, this is still a very abstract approach. So, for example, I explained that this winning probability in this specific game is much better than the winning probability in the deterministic situation. But it was simple enough to devise the concrete model of doing things. But in other cases, for example, there was one slide I didn't explain. But for example, if we do the graph coloring games on a fixed the graph called Audemars graph, then we can actually do much better than the classical situation. But that doesn't mean we can find the quantum algorithm or quantum strategy right away. So they just calculated some quantity, saying that in principle we can do much better, but that's another story to find the concrete way of doing it.
Thank you.
But maybe it's difficult to find out.
Well, this example is again simple enough to find the exact operators. But this is, again, the typical situation. So people believe that any physical measurements should be understood as unitary operators, but not vice versa. So even though you write some unitary matrix, it's not guaranteed that you can actually realize in the lab. So in that sense, I would say that it's still the kind of abstract way. So they found the mathematical the model to guarantee the better performance, but that doesn't mean they can do it in the lab right now.
Okay. Other question? Okay, it seems no question. Let's thank the speaker again.
Thank you. Thank you very much.